So welcome back, everyone. So Gunther, whenever you're ready, you can start.
Okay, so we were describing the scattering relation. So you map to a point in the direction of a geodesic, you follow it, assuming non-trapping, and then you map it to the exit point and exit direction. And this is a more general concept than the distance function. If the manifold is simple, then both are equivalent. So to look at the problem of recovering a metric from the scattering relation is more general than the distance function. And you solve both problems at the same time. Okay, but I will add one information to the scattering relation, which is the distance function itself. So this is a length rigidity problem. We take the scattering relation as before, point and direction of a geodesic. We follow it. We map it to the point of exit, direction of exit, and also we take the length of the geodesic. This is denoted by L here. So it's not clear that we actually need that, but for the results that I'm going to talk about. So this is the distance function. So this still is the same. The length relation is the same as knowing the distance function if the manifold is simple. So the length rigidity question is, do the scattering relation and the distance function determine the metric uniquely up to this change of variables that is identity at the boundary, up to the natural obstruction? So we'll tell you some results in this, new results in this direction. So this is an important problem because we don't assume here that there are no caustics, no conjugate points. You may have the behavior of the geodesics coming together. You may have conjugate points, caustics, and so on. It doesn't allow for that, where the condition of simplicity does not allow it. So for non-simple metrics, the length rigidity is the right problem to study. There are several results here I mentioned, but I'm going to concentrate on the results that I obtained with Vashi and Plamen Stefanov and Vashi, which are related to the foliation condition. So the idea is to first consider what's called the partial data problem. So what is the partial data problem? You have information about the distance function only on a part of the boundary. Here we're not considering the scattering relation because locally near a point, given 2 points on the boundary, there is a unique geodesic joining them. Locally, there's no problem to consider the distance function. So suppose we know the distance function on an open subset of the boundary near the point P, can we recover the metric up to, again, the change of variables, which is the identity where you're measuring near P. So this is the partial data problem. So this could be the whole boundary and we're measuring near the boundary. But you only consider part of the geodesics joining the points in the open set where you're considering, not the ones that go the other way. That's why it's called partial data. And the result is that in dimension 3 or higher, if the point P is strictly convex, so I still need that the geodesics joining 2 points stays inside, and the distance is the same, then the metrics are the same up to this isometry, means this change of variables, which is the identity where we have the information on this open subset here. Okay. So you can solve the local problem completely in dimension 3 or higher. Before, the result known was for real analytic metrics. And also not only we have uniqueness in result, but also stability, meaning if the distance function are the same, then the metrics are the same up to this change of variables, which is the identity in the set where you are measuring. Also, we have reconstruction. That means we have a procedure to recover the metric in appropriate coordinates from the distance function. This is the local result. And then how to consider the global problem, not just locally. By the way, the local problem is of interest in its own right, because in many places around the Earth, for instance, we cannot make measurements. In the oceans, we don't have measurements. So it's a natural problem to consider this partial data problem. So here it comes the foliation condition. We do what's called a layer stripping argument. So it's like peeling an onion. You solve the problem locally near the boundary. We know how to do that from the previous result, even constructively. And then if you have that this is foliated by strictly convex surfaces, there is a point which is strictly convex and we can keep marching. And then there is another point and so on, up to nowhere then set, but that doesn't matter for the reconstruction. So you can foliate by strictly convex surfaces, say in dimension 3, or n-1 dimensional manifolds in dimension bigger than 3, then this condition is satisfied. So this is a way to do it, to solve the problem. If I could have the guarantee that when I march in, I solve the problem locally near the boundary, march in, I have a strictly convex point, then I can keep going. But I don't have the guarantee except when I have this foliation condition. The foliation condition is you can start, not necessarily can be like this, like balls. It can be start at the boundary and you foliate this way or this way. It's completely independent of that. So you can foliate in many ways. The idea is that you solve the problem first locally and then you march in. You keep marching in. That's a layer stripping argument. And then in the isotropic case, we first did the isotropic case. That means that doesn't mean in particular that the two metrics are conformal to each other. The particular case of isotropic is 1/c² times identity. And we can take two metrics which are a multiple of each other, and suppose they're strictly convex with respect to both. Assume that can be foliated for one of them. And then if you have that what's called the length relation to be the same, then you have that the metrics are the same. And we also have stability and reconstruction in this case. This is the case that we did first. In this case, you have uniqueness. I repeat again, you don't have this diffeomorphism invariance because, I repeat once more, is you take the pullback of a metric, and if it is conformal to itself, it will have to be, the diffeomorphism will have to be the identity. And this foliation condition is satisfied for many cases, and you don't need to know all the details of this. Non-negative sectional curvature. This is very, you allow for caustics, you allow for conjugate points. Non-negative means that the geodesics come together. There are caustics, many caustics. The idea of the foliation condition is that you're avoiding the caustics at every step. Locally, there are no caustics. So you solve the problem there, and then you continue, and so on and so forth. And also satisfy a simply connected manifold with non-positive, the negative sectional curvature case, and no focal points. But an interesting observation is this is really an analog of the Herglocks and Wicker and surface condition that I mentioned before. Remember, the Herglocks and Wicker and surface condition in the radial case is that this derivative of the radius over the sound speed is positive. This is an increasing function. So the sound speed is increasing with depth. And then they solve the problem in this case. But this is a uniqueness in the case of radial speed. But this is really, since a mysterious condition, that is in fact a geometric condition. You take the standard spheres, with respect to the standard metric, they are strictly convex. Obviously, the spheres are strictly convex. But this condition means that they are strictly convex with respect to this metric as well. So the balls, the spheres satisfy the foliate the manifold in this case. So this is the foliation condition is the right analog of the Herglocks and the Wicker surface condition. Not simplicity. Simplicity, as I pointed out earlier, like in this example, that this satisfies the Herglocks condition, but they are not simple, the second and third one, and allow for caustics. So this is a result that allows to have conjugate points, which is important. This is important. I mean, this is happens all the time that you have caustics or conjugate points of the metric. In the general case, this is actually was published, it was in the archive in 2017, but was just published this year. Took 4 years. So you have a compact Riemannian manifold with strictly convex boundary, and there is a strictly convex function. So you start with 0 on the boundary, and the level sets when f is equal to constant gives you the foliation. So suppose the boundary is strictly convex with respect to both. You have the same length relation, then there is a change of variables, leaving the boundary fixed so that one metric is a pullback of the other. The examples is the same. Strictly convex manifolds of non-negative. I repeat, this is the main striking example. When the curvature is positive, geodesics come together, like in the case of the spheres, you have conjugate points like the north or south pole, and the theorem is still valid.
So Gunther, I have a question. This is Venki. So I understand that the foliation condition is more general than simplicity. But what about the simplicity imply that it satisfies the convex foliation condition? Then the original initial conjecture is.
Okay, I will come to this right now, very soon.
Okay.
This right on this page. So let's come back to the question when it is simple. The boundary rigidity problem is to recover the metric from the distance function, not from the length relation. The length relation is more information, right? So the result we just proved is that a simple manifold satisfying the foliation condition and boundary rigid, right? Because the scattering relation is the same as the distance function, right? For simple manifolds. So simple manifolds on non-negative sectional curvature and non-positive sectional curvature and no focal points that are now there are new examples of manifolds which are boundary rigid. But there is the question that you just ask, to solve completely the Michel's conjecture in dimension 3 or larger, we would like to know whether simple manifolds satisfy the foliation condition. That's the question you were asking, right? Right?
Correct.
And I don't know the answer, and I have asked the question to many geometers. As far as I know, there are no counterexamples to this, not any proofs. So anybody who has an idea of how to do this is a geometric question, whether simple manifolds satisfy the foliation. And this is certainly true in 2 dimensions, but here the issue is in dimension 3 or higher.
So in 2 dimensions, this result is true, is it? That simple manifolds.
In 2 dimensions, it's true. And it's quite easy to prove because you take a point and take, say, a little bit outside, take the geodesic starting from that point, and then they are strictly convex. You can perturb them a little bit to make them strictly convex, and that gives you a foliation. In 2 dimensions, you just need the curves, right?
I see.
But in higher dimension, you need surfaces in dimension 3, say, and we don't know. This is, I think it's a nice question, but I don't. This will close the circle in the sense of solving Michel's conjecture completely. In 2 dimensions is solved. In dimension 3 or higher, we know that simple manifolds satisfying the foliation condition is true. They are boundary rigid, but is this foliation condition automatically satisfied for simple manifolds? My conjecture is actually more general, that you take any strictly convex manifold, non-trapping, then satisfies the foliation condition. But I don't know how to prove it. So anybody has an idea, let me know. Okay, I repeat this, that the foliation condition allows for conjugate points. For instance, the middle picture will be included because the Hercules condition implies the foliation condition. You say if the condition I pointed this out, if this condition is satisfied, then you have the foliation by these balls, by the standard spheres, because are also strictly convex with respect to this. This is really a geometric condition. They were not thinking of Hercules and Wicker and Sophies in that way. They came up with this by trying to invert some Abel transform that shows up, but it's a geometric condition. Okay, so
hi,
let
Gunther.
me, yes.
Yeah, hi Gunther and Sambuddha. I have a question. So,
Yes.
how can you please explain that? How can we avoid the conjugate points using the foliation condition?
How can I avoid?
The conjugate points are the caustics using the foliation condition.
How do I avoid them? Because I go around them. That's why I use dimension 3 or larger. I can go around them because locally we never have conjugate points, right?
Yeah.
If you are near a strictly convex point or a strictly convex boundary, you are near it, there are no conjugate points. There is unique geodesic joining the points. That's a result. So I stop and then I start again.
Okay.
So there might be a conjugate point in total, but I'm avoiding it. It's like there are, there are wells all over the place that you may fall into, or traps. You're avoiding at every stage, you're avoiding the trap.
Right.
By going a little bit, by just going a little bit, right? That's the idea.
So is it true that you are avoiding those geodesics which are actually have conjugate point altogether?
Sorry?
Yeah. So is it true that you are avoiding the geodesics which have the conjugate point at a certain level?
Yes, yes. I'm avoiding totally, because I only take in geodesics joint points in the boundary, right?
I see.
So,
I see.
So I'm avoiding them completely.
I see. Yeah. Thank you.
You're welcome. Yeah, please ask questions. Okay, so let me give an idea of how to prove this, or it's not a simple thing to prove, but the ideas are easy to explain. You saw this, in the lectures of Uhlmann, I suppose, the inversion of the X-ray transform. The X-ray transform is integration of a function along lines. So you take a line with going through the point X in the direction theta, so like x1, and then this has an explicit formula. When you take the normal operator, which is I star denotes the adjoint. You already saw this, I suppose. And then the inverse is the fractional Laplacian. This is another way to solve to find the Radan inversion formula. The inverse Laplacian, you saw probably this in the lectures by Tuhin, is a singular integral operator that can be written as a convolution. And in fact, in particular, I star I is an elliptic pseudo-differential operator of order -1 for the people who know these words. Anyway, the important thing here that I want to emphasize is that the inverse of I on the left is a non-local operator. It involves the square root of the Laplacian. That's non-local. This convolution is a non-local operator, involves contributions from every single point, right? Depends, of course, on F. And in the case that the manifold is simple, you consider the geodesic X-ray transform. I don't know whether Uhlmann talked about this. You integrate a function along a geodesic that goes through the point X in the direction T until the exit time. Tau is the exit time of the geodesic. And there is a theorem that's generalizing this formula of Guillemin originally, and we reprove it in more, get more explicit inversion formulas. This is an elliptic pseudo-differential operator of order -1. Okay, now why not to use this? So what I want to do is do the same for the geodesic transform. Do partial data. But first I'm going to do the partial data for the geodesic transform, not the distance function, the linear problem first, because it's easier, should be easier. So what I want to do is integrate over functions that join points, whose geodesic is joining points near a given point P on the boundary. So locally, just locally. And this is what we consider with Andras-Bacci. So you have the integration of a function along geodesics. It's only the geodesics joining some point P on the boundary, like we had before. And here I'm just considering the linear problem. So you look only at these geodesics. The geodesic joining these points here. You don't consider the geodesics going from the point P to the other side of the boundary, for instance. Okay, so the question is whether this is injective or you can invert it. Okay, so this is known for geodesics intersecting some neighborhood of the point P almost tangentially. So these geodesics known in here, these points, if this is very small neighborhood, they are almost parallel to the tangent. Almost, not necessarily. Okay, so this is called for the X-ray transform when you're integrating along lines. It's called the Helgason support theorem. So you know the integral of a function along lines. Only some lines in a given set can you determine the function in that set. But this was not known for infinity curves, certainly not for geodesics. And then this is what we prove. And this is the key. The idea of the proof of this is the key to solve the first part of the, because this is the linearization. You linearize this problem in the same conformal class. So you take a multiple here. It's exactly the geodesic transform. So if you get an idea how to do the linearized problem, this is non-linear problem, right? The distance function depends non-linearly on the metric G. So I'm just looking at a linearized problem in the conformal class. It gives an idea of, Venki work on this problem, right, Venki? Okay,
Yes.
so we proved this for geodesics, and this was extended by Han-Min, my student at that time, Han-Min Cho, for arbitrary curves, actually, just coming from a Hamiltonian, not necessarily geodesics. And actually, not only that, but you can put arbitrary weights as long as they are not vanishing. You can integrate along weights, for instance, the attenuated geodesic transform is an example of that. So what's the idea of this? The problem to do this locally is that you try to take I star I here, or you have to cut it up because you only have, you only know this for some geodesics, not all geodesics. It's a non-local formula. So even if F is supported in a small neighborhood of a point, in order to invert, you have to go outside the neighborhood because this not because of the non-locality of the inversion. Even in the case of straight lines, and in the case of simple, it's an elliptic pseudo-differential operator. It's non-local either. So the idea is to create an artificial boundary, to fix the domain near the point P, to fix the domain. But that introduces problems that we're going to see, and then we use a calculus called Melrose's scattering calculus to show that this is composed with essentially the adjoint, which is called back projection. By the way, the I star is called the back projection. This formula is the adjoint. It's called the back projection. You go back to the standard space, not the space of lines. It's elliptic in that calculus, and so we can invert it modulo an error which is smooth. And if the domain is small, that error will be small, and then we can using a Neumann series, we can invert. This is very quickly the idea of the proof. So this is the situation. So why is this not the same as the inversion formulas? Again, I create an artificial boundary which is strictly convex, like this. This is created, it's artificial, totally artificial. Where are we going to put it will depend on the size of this domain. Yeah, now we take geodesics joining points in the boundary, and then for a given point, you have a cone of geodesics, right? When you join these points here, the geodesics going from here to here, you are not taking into account, remember. And then the problem is that cone degenerates as you approach the artificial boundary. And it becomes just tangent here. So the cone is getting smaller, narrower, narrower, narrower. And how narrow it is proportional to the distance to the artificial boundary. X is the distance to the artificial boundary. And you can write it down. So this is, we make a cutoff here to take into account only the geodesics joining points in this neighborhood, which are almost parallel. So it's a smooth cutoff, not to consider all the geodesics. And then we apply the back projection, right, start. And we can write them explicitly, but it is singular now. At the point C, these are all the directions here. This is the X-ray transform with the geodesics. This is the cutoff, and this is 1 over the distance squared. This integral is convergent. The question
so,
is,
Gunther, I have a,
yes.
So the thing is, in the previous result that you mentioned, that actually the same result, it's not valid in 2 dimensions.
Which one?
Or it's the inverting the local geodesic X-ray transform, right? And even what
this one, this
result.
This one that I mentioned here. No, it's not that it's not known. We don't know it. The same result is not known in 2 dimensions. This
so yesterday. But there is also this Bowman's counter example, right? And yesterday also Plamen talked about this.
But that's for general weights, right? So the result of Han-Min Cho is in dimension 3 or larger, not in 2 dimensions, where you can put more general curves and more general weights. In 2 dimensions, the expectation is that for geodesics, it will be true. It might not be true in general, because there are these counterexamples of Bowman. But for geodesics, I believe it will be true. Does that answer your question?
Okay, yeah.
So it's a much more delicate issue in 2 dimensions. Okay. So this is a very interesting question, whether in 2 dimensions this transform is locally injective, in the sense there is a Helgason support theorem for this, where you consider geodesics only joining points, and it's clearly not like here, where in dimension 3 or higher we have more freedom. We have more freedom to choose our geodesics, and in dimension 2 you don't have much freedom. So the inversion of this is likely to be a much more delicate issue in 2 dimensions. This is a problem I have been working on. I don't have an answer. I'm sure other people are working on it too. So it's not known in 2 dimensions. The counterexample of Bowman does not preclude geodesics. Precludes general weights, right? Is that clear? Venki?
Yes. Yeah. Yes.
Okay. And then the thing is to show there is a calculus called, I will explain this a little bit, the calculus in a minute. This is the most technical part of my talk, but I think it's good to explain because it's I mean that's the whole. It's an elliptic pseudo-differential operator, like we had before, elliptic pseudo-differential operator for simple, but this is in this calculus. This calculus that deals with degenerate. This case, these cones are degenerating at the boundary. Why it's called scattering? Because you change x to 1 over x. So instead of taking the distance to the boundary, you're going to infinity. So it's like a scattering problem, going to infinity by changing x to 1 over x. So this is 1 over x squared. So you see here. And then this operator is invertible. It's an elliptic pseudo-differential operator in this calculus, and this calculus tells you there is an inverse on the left. So you get the identity plus a remainder, but the remainder is smooth, has a smooth kernel. But if you are close to this domain has a small size, it's a small, you can show that the norm of this is small. And the identity plus an operator of a small norm is invertible by using a Neumann series. And you can identity plus R, if the norm of R is small, is invertible. So you can invert P, you can invert P, you can invert I, and that's what we wanted to do. So not only you get uniqueness, but you get an inversion formula. It's not exactly like in Radon's formula because you have this Neumann series, identity plus R inverse, but it's quite explicit. Okay, so let's see how I'm doing on time. Okay. We did some numerical experiments with this, by the way. My co-authors did the numerics. Some sound speed and then some different functions, and it works quite well. So it depends on the number of iterations. As I said, the name Neumann series, N means the Neumann series. As you increase in the Neumann series, the accuracy gets better and better for this. Okay, I think I will explain before I explain the second part, the scattering calculus, very quickly. This was Melrose in 91, but there were already calculus like this in Hormander and Parente and Chubin. And instead of having the usual estimates of pseudo-differential operators, when Z is in a compact set, is like 1 plus modulo C squared to the M minus beta. When you differentiate with respect to beta, you lose. That's the standard calculus. You also look at the behavior at infinity. So as I said, you have a scattering, you change x to 1 over x. So the symbols, you look at both the behavior in x and the behavior in the dual variable zeta. So there is 2 indices here, one to indicate the order of decay in x and the order of decay in C. That's why it's called scattering, because it looks at the behavior at infinity. Okay, so I just wanted to explain, I'm not going to talk more about this. But the important thing is that this is there's a calculus for this, and you can invert elliptic operators. You have to show that the symbol is non-zero to invert these operators in this calculus. Okay. So now let me go back to this is a linearized problem. It doesn't solve the problem for the nonlinear map. This was we only consider the linearization of this in the same conformal class. So it's of interest in its own right how to invert the geodesic transform locally. I mean, to get an Helgason support theorem. But doesn't solve the problem for the nonlinear map. There is a way we can do this using what's called pseudolinearization. You transform it into something that's almost linear transform. So you have two metrics, G1 and G2. So let me explain. So X denotes the Hamiltonian. Remember, we have the Hamiltonian the bicharacteristic curves for the metric G2, we have the integral curves of the Hamiltonian vector field before. So you start, T is the travel time for the metric G1. Okay, so you start S time for the metric G1. Again, you're working in phase space. And the rest of the time you go with the metric G2. You consider this function. So why is that? Because at 0, when S is equal to 0, here is you have the starting point and you have xg2 of t of x0. And when S is equal to t, you get the first one. And we know, now we take the fundamental theorem of calculus. The integration of the derivatives is the endpoint minus the f of t minus f of 0 is this. And so now you have to do this differentiation and you get a very nice identity. You get this matrix and V denoted the Hamiltonian vector field. And is equal to the difference of the matrix. So this is the integration along the geodesics for G1 of the difference of the Hamiltonian vector fields, and this is a non-singular matrix in the case that the boundary is strictly convex. So you have to invert. The problem is reduced to inverting this transform. So this is what we know. xg1 is the endpoint of the geodesic and the direction, g1, and this is the endpoint of the geodesic g2 with direction x0. x0 is a point and a direction. Capital X0 indicates a point and a direction. So this is a nice identity just obtained by the fundamental theorem of calculus. And these are the two vector fields and so on. So the problem is we really want to get this. This is just some weight, and the right-hand side is what is known. In particular, this is for the injectivity, this is 0. The right-hand side is 0, so you want to invert this transform with weights. So it's reduced to more or less a linear problem. That's why it's called pseudo-linearization, this procedure. It's very useful in many instances. We have used it in many ways. So we have this identity. This is the Hamiltonian vector field. For instance, in the case that the metric is isotropic, then the vector fields are these ones. So VG1 minus VG2 is linear in the sound speed square, C1 square minus C2 square. So you want to invert that So it's linear in CK squared. That's the idea of this identity. And we use the ideas of the paper with Vashi to invert this transform. It's not exactly the same because we have weights here and so on, but it's the same idea. And this gives you a reconstruction method even. For instance, in the case of the sound speed, this is what this is. And this is the data. G2, you can take it anything that you like for the reconstruction. We're trying to find G1. G2, you can take it to be the Euclidean metric, for instance, sound speed 1 in this case. And you can invert this transform. So it's reduced essentially to an inversion of a weighted geodesic transform. And we use the methods that we introduced before. So that's the two ideas are this inversion of this transform locally, and then this pseudolinearization, which you can apply to any flow. You can flow not only a geodesic flow here, this is geodesics, you can take other flows. The same idea leads to this type of formulas, which are linear in the difference of the Hamiltonian vector fields. Okay, and then for the nonlinear problem, the same authors did numerical experiments, which is the Marmousi model, which is a benchmark in geophysics. You want to try an algorithm. This is in 3 dimensions. So you take a section of the Marmousi model. It's very complicated. It has very complicated sound speed. This is done so you can test any algorithm. And it performs very well. This again is the Neumann series steps, the larger, and even with noisy data, it performs pretty well. This is a very complicated sound speed. Certainly has caustics and many other things, trapping, and so on. Okay, so to finish, let me come back to this, because I have described two problems. One is to recover a metric from the Dirichlet to Neumann map, or the voltage to current map, and the other one from the distance function or the scattering relation. But I think these two problems are related, and this relation was found, some relation was found in this paper with Pestov, in the two-dimensional Riemannian manifold with boundary, which are simple or boundary rigid. This is Michel's conjecture in 2 dimensions. How is that? Is to show that from the distance function, again, if it is simple, it's the same as the scattering relation. Right? These are equivalent if the manifold is simple, but from the scattering relation in the simple case, we can recover the Dirichlet to Neumann map. That's the key thing. So we know the distance function, then we can recover the Dirichlet to Neumann map if the manifold is simple. So those problems that look very different when the distance function is travel time of waves. These has to do with electrical currents. They are related. And I think there is even more relation that we haven't found yet. So how is the proof goes? So if the distance functions are the same, this is in dimension 2 only, the Dirichlet to Neumann maps are the same, and by the result I mentioned very early on with Lassas, then one metric is conformal multiple of the pullback of the other one. In 2 dimensions, we know everything about the Dirichlet to Neumann map. with a change of variables, which is the identity of the boundary. So we have this. But now Mohammed's result, this should be G2 here, says that the conformal multiple must be 1. As the conformal multiple, this is the result I mentioned before for isotropic metrics. Then G1 must be equal to size, if beta is 1, size star of G2. So this is the idea of the proof. But to show this, that you can regard the Dirichlet map from the distance function, one uses that the back projection is onto, is surjective. And this follows by showing that the geodesic transform is injective. And we knew that for the geodesic transform, for simple manifolds. This geodesic transform is invertible for simple manifolds. And the range is closed because this is a pseudo-differential operator and therefore Fredholm. So the range is closed. And so this is very briefly the. Of course, there is a lot to prove here. I have not given the details of this. I just wanted to point out that these two problems that look very different, they are related. So let me make that relation a little bit more explicit. On the left, you have the Dirichlet map that in some sense can be considered as a quantum object. It's an operator. But the operator has a kernel and depends on 2n-2 variables. It's the boundary across the boundary. The distance function also depends on 2n-2 variables. It's n-1 plus n-1 is 2n-2. So there are no asymptotics really to go from one to the other. The Dirichlet map is defined using harmonic functions and is via this quadratic form. Remember, the quadratic form and the Dirichlet map are equivalent. This is also called Dirichlet integral. Is the power that you need to maintain the potential F on the boundary. Is the infimum of this quadratic form over all the functions that have this boundary value. Actually, this is a way to solve the Dirichlet problem by finding the infimum of all the functions sufficiently regular that give you F on the boundary, and then that's the U. And the distance function is also obtained as the infimum of the lengths of some functional, and this is in finite dimensions, is curves. As some functional, you find the infimum of the lengths of all the curves. So curves corresponds to functions. Curves on the right corresponds to functions on the left, and geodesics correspond to harmonic functions. This is very roughly the correspondence. And by looking at these quadratic forms, you can show that the problem is invariant on the changes of variables. Both problems have the same abstraction. You take a diffeomorphism, which is the identity of the boundary, they have exactly the same abstraction. Now I look at the scattering relation, which is related to the distance function. Here is the definition, is a plus sign, by the way. Here is. And the scattering relation is solving an ODE. You take the Hamiltonian, you take these curves, you know the initial point of the ODE, the final, the initial point and direction. So you have the initial conditions of the ODE, and you know the final conditions, including the time. So you know this. So this is a finite dimensional problem. It's solving ODEs. Here you're solving PDE. So this is what I said. This is a problem in finite dimensions, and this is an infinite dimension. Yeah, this is the last remark is for the people who know about this, but so I'm not going to make much more emphasis on this. Is the graph of the Dirichlet map F, and is a Lagrangian manifold in infinite dimensions. and the symplectic form is given in terms of Green's theorem. Is G1 F2 minus G2 F1. And the scattering relation is you projected on the boundary is a Lagrangian manifold. This is technical, but it's an interesting connection. It's a Lagrangian manifold on the cotangent of the boundary across the boundary. And don't pay attention to this if you don't know the words. There is some connection. So to finish, let me mention that we have had a connection between the distance function and the Dirichlet-Neumann map if the manifold is simple. Because we needed that the geodesic transform is injective. That's the main thing that we use, or the adjoint is onto. Is there a connection for when you have caustics between the scattering relation and the Dirichlet-Neumann map? In 2 dimensions, we don't know that. And in 3 dimensions, actually, you want to go the other way because we know a lot about the distance function or the scattering relation. Remember, if the foliation condition is satisfied, we can solve the problem. But for the left, for the Dirichlet-Neumann map, the only case that we really know is a real analytic case. For instance, we don't even know a simpler question. Suppose the Dirichlet-Neumann map is the same as the Euclidean, as the Dirichlet-Neumann map of the function 1, the Euclidean case 1. Is it true that this is the pullback of the Euclidean metric? This is certainly known for the distance function. This is Gromov result. If the distance function is the same as the distance function of the Euclidean metric, must be pullback of the Euclidean. So is there any way to go from the left to the right? That will be a way to solve this problem of recovering the metric from the Dirichlet-Neumann map, because we know a lot about this, at least when the foliation condition is satisfied. We don't know that I have been trying to do this for a long time without success. I hope some of you can do this. I don't want to take this problem to my tomb, and I leave you with that. Okay, thank you.
Thank you, Gunther. Any questions? So I have a few questions, Gunther. So what about the other way? That is, so for instance, as far as I understand, in the 2D case, if you have that the boundary distances are the same, then the Dirichlet-Neumann maps are the same. But is that also valid in higher dimensions?
Only in the simple case.
Yeah, so I'm only considering the simple case.
Yes.
So what about in higher dimensions? Is that true?
We don't know that. But that wouldn't be so interesting because you wouldn't get any result, right?
Okay, yeah, because you're saying that because more is known about the distance function rather than about the Dirichlet-Neumann map.
Right, exactly. In dimension 3 or higher, we know a lot about the distance function or the scattering relation. We know that if the foliation condition is satisfied, we can determine the metric up to this obstruction. We have no idea, even in the simple case, about that for the Dirichlet-Neumann map. So, you know, I don't know the answer to your question, whether you can go there from the distance function to the Dirichlet-Neumann map, but that will not be so interesting. You wouldn't get anything, right?
Mm-hmm. I see.
Even as I said, even here, a simpler question where you have the same measurements as 1. Can you conclude that this is the pullback of 1? We don't know that either.
I see. So the other question is so if I understand your recent paper with Plamen and this one on the boundary rigidity problem, right? That actually is a local, you actually solve a local question.
Yes.
Correct, in 3 dimensions and higher. But because you know that the 2D case, it's completely solved. Is it so? Can a local question be addressed in the 2D case?
Not with these methods. We use this fact that this is an elliptic pseudo-differential operator in this calculus, and that's not the case in dimension 2. Yeah. So the local question in dimension 2 is very interesting, but it's not, this method doesn't give it.
So the reason why this method is not giving is because you relate the boundary distance function using the pseudo-linearization technique to the weighted geodesic X-ray transform.
Yeah, that right? that's one reason. But even if you want to look just at the geodesic transform, forget about the distance function. Suppose you know the integral of the geodesics on this part is 0, is the function 0 here. We don't know that. It has nothing to do with the distance function. Just the Helgason support theorem in 2 dimensions for geodesics. We don't know that.
And the third question that I have is that in the convex foliation condition, right? So you said this layer stripping type of algorithm, but what prevents this, the annular region to shrink to 0 before you actually reach the center?
Well, no, you have to prove that. I mean, this is part of the. This is part of the proof that you can keep going.
So that
except for a point, you can get everything. No, it's not.
I see.
You will only end up if it happens that you have trapping, for instance. This condition, the foliation condition, does not allow for trapping. You can show that the geodesics are not trapped in this case. If you suppose you have trapping in some region, then you will not be able to continue. But otherwise, you can continue as long as the foliation condition is satisfied. But you have to prove it. I mean, it's not that you can keep going, right? I mean, you can.
I see.
Because this could have a limit point before you get to the center, right? It's, the paper is 90 pages long, not for a reason.
I see. Yeah. Any other questions from the audience?
Except for you are the only one asking questions, and some Buddha. What about the younger generation there? Okay, well, I hope I can meet some of you guys sometime.
I have a question.
Who?
Some Buddha.
Some Buddha. Well, somebody else asking questions about that. Okay, some Buddha, what's the question?
Yeah, the question is that so non-trapping is one condition that will interrupt this going inside in the foliation condition, right? So
yeah, well, if you have trapping, then the foliation condition is not satisfied. Yes.
Yeah. So, is there any other condition?
That we don't know that. As I said, my conjecture is that if you have a strictly convex manifold and it's non-trapping, then the foliation condition is satisfied.
I see.
But I don't have a proof nor a counterexample.
Yeah.
This is a problem for some of you guys. You need to solve these problems. I'm too old.
Any other questions? If not, thank you very much, Gunther, for the wonderful set of 2 lectures. And I hope to see you sometime soon in person. So take care.
Yeah, I have been giving talks in person. I have given like 4 or 5 recently,
I see.
but not
But you are,
abroad. I still haven't taken the step of going abroad. Yes, within the
right.
US. Okay.
Yeah. Okay. Thank you very much, Gunther, once again.
Good night. Good morning for you. Good night for me.
Yeah. Good night. Take care. Bye-bye.
Okay, bye.
Bye-bye.